Hello friends, welcome you all to the 29th lecture on function analysis and its applications. In this lecture, we will discuss the continuity of inner product, parallelogram law and polarization identity. These are the contents of today's lecture. Continuity of inner product, parallelogram law, polarization identity. Theorem. Let X be an inner product space and xy be vectors in X, then X is equal to Y if and only if inner product of xz equal to inner product of yz for all z belonging to X. Proof. Let X is equal to Y. Then for every z in X, we have inner product of xz equal to inner product of yz. Okay. So putting if X is equal to Y, then for every z in X. Okay. So X is equal to Y, that is inner product of yz, and equal to inner product of yz. That is for X is equal to Y, this is equal. Conversely, if inner product of xz equal to inner product of yz, then we have to prove X is equal to Y for all z belonging to X. So we have inner product of xz equal to inner product of yz, then inner product of xz minus inner product of yz is equal to 0. Okay, this in left side. This implies that using the force property of inner product, we have inner product of x minus y z equal to 0. Okay, and we know that for any z belonging to X, suppose P x equal to 0. Okay, for all x belonging to X and P is the element of X. Okay, so for all x belonging to X, inner product of P x equal to 0, that is P is equal to 0. Okay, so here inner product of x minus y z is equal to 0. It means inner product of x minus y equal to 0, that is by this property x minus y equal to 0, that is x is equal to y. Theorem is proved. Next theorem. In an inner product space, the inner product is jointly continuous. That is, if xn converges to x and yn converges to y, then inner product of xn, yn converges to inner product of xy as n tend to infinity, where xn, yn, xy all are the member of inner product space. Okay, proof. Mod of inner product of xn, yn minus inner product of xy. Okay, if we prove this converges to 0, that is inner product of xn, yn converges to inner product of xy. This. Okay, so let us prove it. Mod of inner product of xn, yn minus inner product of xy. Okay, in this we added inner product of xny and subtracted inner product of xny. Okay, that is there is no change. Okay, so taking these two as one term and these two as one term. Okay, so we know that mod x plus y less or equal to mod x plus mod y. So using that property, this is less or equal to mod of the inner product of xn yn minus inner product of xn y plus mod of the inner product of xn y minus inner product of xy. So using the force property of inner product, this can be written as inner product of xn yn minus y. Okay, and this term can be written as inner product of xn minus x y. So by Schwarz inequality, this can be written as norm of xn into norm of yn minus y, and this by Schwarz inequality, norm xn minus x into norm y. Okay, so in statement here, xn converges to x and yn converges to y. Okay, that is norm of yn minus y tend to 0, and norm xn minus x also tend to 0. Okay, so total tend to 0. Okay, here therefore mod of inner product of xn yn minus inner product of xy tend to 0 as n tend to infinity, because xn converges to x and yn converges to y. Thus inner product of xn yn converges to inner product of xy. Hence in inner product space, the inner product is jointly continuous. Next theorem, Schwarz inequality using the Cauchy's inequality. For inner product space L to n, use Cauchy's inequality to prove Schwarz inequality. Okay. Let x is equal to n tuples of x1, x2 and so on xn, and y is equal to n tuples of y1, y2 and so on yn, be any two members of the inner product space L to n. So by Cauchy's inequality we have, okay, summation I is equal to 1 to n mod xi yi less or equal to summation I is equal to 1 to n mod xi square whole power 1 by 2 into summation I is equal to 1 to n mod yi square whole power 1 by 2. Okay, this is the Cauchy's inequality. What is Cauchy's inequality? This is the Holder's inequality for p is equal to 2. Now, by the definition of inner product on L to n, we have inner product of xy equal to summation I is equal to 1 to n xi yi bar. So, taking modulus of both sides, we have this, and this is less or equal to summation I is equal to 1 to n mod xi yi bar. So, mod xi and mod yi bar. Mod yi bar, that is mod y. So, this can be written as summation I is equal to 1 to n mod xi mod yi. Okay. So, using this, we have this is less or equal to summation I is equal to 1 to n mod xi square whole power 1 by 2 into summation I is equal to 1 to n mod yi square whole power 1 by 2. What is this? This is norm x and this is norm y. So, mod of the inner product of xy less or equal to norm x norm y, which is Schwarz inequality. Next theorem, if x and y are any two vectors in inner product space, then norm x plus y square plus norm x minus y square equal to 2 into norm x square plus norm y square, which is known as parallelogram law. And another norm x plus y square minus norm of x minus y square equal to 4 real part of inner product of xy. And 4 into inner product of xy equal to square of the norm of x plus y minus square of the norm of x minus y plus I into square of norm x plus iy minus I into square of the norm of x minus iy, which is known as polarization identity. Let us prove it. First, parallelogram law. This is inner product space. Okay. And inner product space. Okay. So Hilbert space also inner product space. Okay. So Hilbert space we will discuss later on. Okay. If x and y are any two vectors in an inner product space, then norm x plus y square equal to, this can be written as inner product of x plus y, using the force property of inner product. This can be written as x plus y plus inner product of y and x plus y. Again, using the force property, this inner product of xx plus inner product of xy plus inner product of yx plus inner product of yy. This can be written as norm of x square plus inner product of xy plus inner product of yx plus norm of y square. Equation 1. Similarly, square of norm x minus y, it is also written as inner product of x minus y. So using force property of inner product, we can write inner product of x minus y plus inner product of minus y and x minus y. Okay. So this can be written as inner product of minus y x minus y, because inner product of alpha x y equal to alpha xy. So alpha here minus 1. So we can write this one. This is as it is. Again, using the force property of inner product, this can be written as inner product of xx minus inner product of xy minus inner product of yx, and this is minus and this minus, that is plus inner product of yy. Okay, this is very simple. And inner product of x's, that is norm of x square, and this is as it is minus inner product of xy, and this is as it is also minus inner product of yx, and this is norm of y square. Equation 2. Adding equation 1 and 2, we have norm of x plus y square plus norm of x minus y square equal to 2 into norm of x square plus norm of y square. Okay. So this is equation 1, adding 1 and 2. This cancelled out by this. So we have this one. First proved. To prove second, we subtract equation 2 from 1. We have square of norm of x plus y minus square of the norm x minus y equal to 2 inner product of xy plus 2 inner product of yx. So inner product of yx can be written as conjugate complex of the inner product of xy. Okay? By second property of inner product. This can be written as 2 into 2 real part of the inner product of xy, because we know that z plus z bar is equal to 2 real part of z. Okay. So norm of x plus y square minus norm of x minus y square is equal to 4 real part of the inner product of xy. Third, polarization identity. Now by replacing y by iy in equation 3. Okay, so we can write this is square of the norm of x plus iy minus square of the norm of x minus iy equal to 2 inner product of x iy plus 2 inner product of iy x. Again, apply the property alpha x y equal to alpha xy and x beta y equal to beta bar xy. So this, by this property, write 2 I bar inner product of xy, and this is 2 I inner product of yx. Okay, I bar means minus I, that is minus 2I inner product of xy plus 2I into inner product of yx. Multiplying both sides of 4 by I, okay, we get I square of the norm x plus iy minus I into square of the norm x minus iy equal to minus 2I square inner product of xy. Okay, here multiplying I plus 2I square inner product of yx. So I square is equal to minus 1, that is this is 2 into inner product of xy minus 2 inner product of yx. Adding equation 3, this is equation 3 and 5. We have square of the norm of x plus y minus square of the norm of x minus y plus I square of the norm of x plus iy minus I square of the norm x minus iy equal to 4 inner product of xy, because this is minus and in equation 3 this is plus, cancel out. So 2 inner product of xy from here and 2 inner product of xy from here, we have 4 inner product of xy. So this is known as polarization identity. Hence, this completes the proof of theorem. Noting point: the name of parallelogram equality is suggested by elementary geometry, where we know that in parallelogram norm, the sum of the square of the diagonals equals the sum of the squares of the sides. We consider the norm as the length of the vector, then this result may be interpreted as parallelogram line r square. If norm does not satisfy the parallelogram equality, they cannot be generated by inner product. This is the parallelogram. So suppose this is the vector x, okay? This is as vector x, and this is as vector y. Okay, this one and this. So this is x plus y vector. Okay, and this one, and this is y. So corresponding we have this is y vector. Okay, so this is y and this is x. So this one is as vector x minus y. This is x and this is this one. So this is the x minus y. Okay. So magnitude of this value, that is norm of x, and magnitude of this, that is norm of y. Again, this is the magnitude of this side, that is norm of x, and this is norm of y, and diagonal this. This is the vector x minus y. Okay. So magnitude of this value is norm of x minus y, and this is the x plus y vector. So this is magnitude value of this one. So this is the parallelogram law. This is the magnitude value of the sides. So we know the property of parallelogram law. The sum of the square of the diagonals equals to the sum of the square of its sides. That is this. The square of the norm of x plus y, that is diagonals 1, and this is the norm of x minus y, that is diagonal second. The sum of the square of the diagonals equal to the sum of the square of sides. Due to this reason, we called it is a parallelogram law. In this lecture, we have discussed the continuity of inner product, parallelogram law, and polarization identity. These are the references which have been used in this lecture. Function analysis, Dover publications written by George Beckman and Lawrence Naresi. Second, function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by V.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.